All right, so how you guys doing today? Okay, so we have an exam on Wednesday and Friday in here. We'll have another review session today as well. So if you keep watching the review sessions or other lectures on YouTube channel, you have a very good idea what you might see on the exam. So let's also spend some time on the review. Okay? So we've been talking about the theories of the reaction before. Okay? So let's try this one, another one here. Well, actually, this is the one we tried, but I want to do this again. So yeah, I'll give you about 1 or 2 minutes. You can try to do this one real quick. There's something I want to tell you today. So that's why we're doing this again. This is what we did on Friday for the last problem. We tried together. So here's our direction. We have about 30 seconds. Okay, so let's do this together. So we're gonna do this one. I hope you guys remember this one again. So I'm gonna link these two. So we do this one. Over here. But the point is, you need to know much about the stereochemistry wise. So you need to remember there's a implied hydrogen there, because you see this carbon double bond with another carbon. So there should be the one hydrogen for each carbon in this double bond, but just implied there, because we don't normally show the hydrogen on the structure. So anyway, if you do this one, this is something that you see, but stereochemistry wise, this is what happening. Okay, so because you see this two groups on this double bond is on the same side and hydrogens as well. So when they do their order cycle addition, they will do also put them on the same side as well. So this is why you see those hydrogens are kept on the same side here, up and down from your cyclic compound base. Okay, so this is the something I want you to remember. So because they are in the same side, hydrogens and those two groups on this double bond, they also stay on the same side, hydrogens and the two groups over here. So let's try this one. Okay. So this is what we did before. Let's try to change the position here. Okay. Try to change the more like a transform here, like E, like an E form, and send what might be the answer. Okay. So another minute here, 1 or 2 minutes. So now they're in a different side, okay? That's what you need to remember. Okay, about 1 minute. Okay, about 30 seconds. So it is important for you to just try. It is okay because this is a review session today. You only need to get the right answer on the exam day. So let's try it out and see. You can compare your answer to the one we're gonna do together, and then it will make more sense. So yeah, this is also pretty much the same product, but slightly different on the position of these two because they are now on the opposite side. So this is going to be here. So if you have this one over here, you're going to have those two on the same side. It's this one, and this one, and this one, and this one. Okay. So these two will be the same side. So I put those on this wedge, so they can put on the same side. And we can do the dash line to put them on the back from this base. So we'll be here. Okay. So this is the something I want you to distinguish. Either you have like a seesaw trans product from E and Z Dynafire. So this is kind of something you may see on the exam. Okay? So try to look at the groups on the double bond where they are. If it's opposite side, you have some trans products. If it's on the same side, it could have been a cis product we just did like 2 minutes ago. Okay? All right, let's go. All right, so there's also another one we talked on Friday, but let's do this together again, but slightly different way. Okay? So the read it this way. So we're gonna do the same chemical reactions with the diane, but at different temperature. And you can just try to draw the major product at two different the environments. The one is the 0 Celsius degree, and the other one is 40 Celsius degree. So this is the one thing you need to think about: the kinetic control and thermodynamic control. Okay, so try to think about the major products of these two scenarios. So if it's the kinetically controlled, thermodynamically controlled, which product between two possible products will be major? It is about 2 minutes. 2 minutes. Try to draw those products first, and you can compare them to the one we're gonna do. Okay, 1 minute. Okay, 30 seconds. Okay, so let's do it together. So when it is 0 Celsius degree, this will be kinetic or thermodynamic? Could you guys tell me? Kinetic, perfect. Kinetic. So when it's kinetically controlled, you just need to think about the 1-2 addition. Okay. And when it's the high temperature, we're gonna call this thermodynamic control. So in this case, we're going to think about 1 and 4 addition. So in these two different scenarios, your major product will be looks like this. this is 1, 2. You see the 1, 2. And if it's thermodynamic control, your major part will be this one. 1 and 4. 1 and 2. Okay, I want you to remember this one. Okay, so low temperature, kinetic control, and if it's high temperature, thermodynamic control. So obviously this is more stable than this one because it's a more substitute double bond you have in the compounds. So that is why it takes more energy to make this more stable product. But if it's in the high temperature, we have no problem because we have a lot of energy available for the compound given into the even furtherly more stable compound. So that is why it's favored in the more frequently happening at the high temperature. But if it's not, they just settle with the kinetic major product. Okay, let's move on. Okay, so the next one is here. You have an observance value, it's about 0.40, and you have epsilon molar absorptivity number is about 2.0 times 10 to 5. And then your path length is just about 1 centimeter. In this case, if you use the UV spectroscopy, one might be the concentration molarity. So as we did before, try to do this one. About 3 minutes. This is take some time. But 3 minutes. So by the way, you need to bring your calculator, right? Okay. So make sure you guys bring a calculator. But do not bring the calculator with a very big screen. Like just bring the real cheap one. Okay, about 2 minutes. 1 or 2 minutes. Yeah, use your calculator is okay. Because if you practice that with the calculator, it will save your time on the exam because you know how to use the calculator. Okay, about 1 minute, and we can do this together. Right. Try to do this with your calculator, so you know how to use the calculator to get this calculation work done, and you get this. Okay, about 30 seconds. Okay, so let's do this together real quick. So if you look at this one over here, the one we did was we tried to flip this one over, these two. Okay, so if you do that, it will become this. Okay, you guys know this one, right? So when you get to this one, just by flipping them over, what we did before was we tried to multiply the denominator over here, right? A, then you can be cancel, right? If you A, so you have this is cancel, right? And A times 1 is A, right? And then you can divide this one by L, okay? L, right? Then it's gone, right? That means, yeah, this one. So whenever, this will be in the exam for sure, 100%. So you can definitely say concentration should be equal to observance value over molar absorptivity times Pascal length. So you can use this one, it will be easier for you to calculate. Because you need to just put the numbers here and divide that number by this one and this one. Which this is just the 1 centimeter, normally no problem, but so your observance value divided by molar objectivity value is your answer. It's easier this way, right? So if you do this one, you have a 0.40 over this one, 2.0 times 10 to fifths, okay? Times 1 centimeter, 1.0 centimeter. But you know, I'm not gonna care about this one much, it's just one. And then this is the same as what? 0.40 is the same as 4.0 times 10 to negative 1. Okay? So if you switch this one to in here, it's even easier because it's a 4 times 10 to negative 1 over 2 times 10 to fifth. So 4 over 2 is what? 4 over 2 is what? 2, right? Perfect. It's 4 divided by 2. So you can just copy this one too. And here, your exponential number wise, this is a negative 1 minus negative 5. I'm sorry, minus 5. Because this is a division. So when it's multiplying, do you guys know this, right? Exponential number plus that number. When it's a multiply. But when you're dividing that number by, you just need to negative 1 minus 5, because it's 5. So 10 to negative 1 minus 5 is what? Negative 6. So in this case, you might need it, you might don't even need a calculator, because, but yeah. So anyway, but you can use a calculator anyway. So this is the answer. So if you do the number in this way, it will be a lot easier. Okay? So this is one trick you can do. Just put the numbers and the observance value on the top, and put the molar objectivity value at the bottom. Path length is always 1 centimeter. I'm not going to change it because your cubit is set to 1 centimeter. So there's no way I'm going to change 1 centimeter to anything else. So just that divided by that, the answer. So it will be much easier than this one. Make sense, right? Okay? Let's move on. All right. So next one. Oh, so this is a good one to try. So can you guys name this compound? And you need to think about this as your base. I'll give you 1 minute. So there's a benzene ring, and you have a hydroxy group attached to it, and we have a specific name for it. Okay? I hope you guys remember this. And then you add an addition group. Okay, 30 seconds. Okay, so what might be the answer? Could you guys tell me? So What is this, by the way? Phenol, perfect. Phenol, right? Okay. So you can start from here, and additionally, you have two groups here as your prefix. So you have two, but this is your base. So you're gonna count this one as one, because this is your base that you hydrogen group as your point. 1, 2, 3, 4, 5. Okay. So it'll be 2 and 5. So 2, 5 dimethyl phenol. Okay. So the most important thing is the base, your benzene related analog base. Okay. All right. Let's try another one. This is this one. This is about 1 or 2 minutes. Oh, and in here we're gonna. This is your base. So benzene ring and one methyl group is attached to it. If you guys remember, it's a toluene. Okay? So toluene is your base, and you have a 3 nitro groups. Nitro groups, 3 nitro groups, and it's attached to a toluene. That makes it much easier name. Okay, 30 seconds. Okay, so once again, because of this one is our base, we count from here. 1, 2, 3, 4, 5, 6. Okay, so you can say 2, 4, 6. There will be 3, right? So we'll put tri. Okay, nitro toluene. So there might be the good name for it. Okay. So the first thing what you need to do is try to find out the base first, the specific name for it, and you can name this the prefix at the okay. Okay, this one. And your base is right here. It's the aldehyde groups attached to your benzene ring. And this is the one that we talked, the first compound in the text. Okay. So what might be the answer? So this is what we call benzaldehyde. Because so this is simply aldehyde, but it's the benzene, so benzaldehyde. And you have a chlorine on here. You can say 1, 2, 3, 4, but there's a better name for it. If you guys remember this, we can put para chloro benzaldehyde. Okay. So para means it's on the opposite here. Okay. If it's in here, it'll be author. Author. Okay. If it's in here, it's meta. Okay. So if the chlorine was here, it could have been what? Orthochlorobenzaldehyde. If the chloro would have been here, it could have been what? The meta-chlorobenzaldehyde. But now in the opposite position, which we call this para-chlorobenzaldehyde. So if you say 4-chlorobenzaldehyde, I might say, oh, it's reasonable. But we have the specific term that we know in the position. So you can say para-chlorobenzaldehyde would be much better. Okay, I'll give you one more example. Maybe you can. So for example, if you have this one, you can say what? 1,2-dichlorobenzene, but another way, what we can say? It's ortho-dichlorobenzene. It's the same thing, but if you know there's a specific term, it makes much easier and simpler better. Because you don't have to say it's 1,2. If you just say ortho, they just people know, oh, it's 1,2. Okay, just one more. So how about this one? Okay, so this is obviously ortho para, but here meta. Meta dimethyl benzene. If you guys remember this, there'd be even better way to say this. If you have two methyl groups on the benzene ring, you can call them xylene. So it's a meta-xylene actually, but it is okay. You can say meta-dimethylbenzene is perfectly right, but once again, if you have a better, shorter, easier name, you can just say meta-xylene. That's even better, I guess. But as long as you can name this compound correctly, I'll give you full credit anyway. So don't worry about too much, but just remember there's a specific term you can also do alternatively. Makes sense, right? Okay. All right. Then, okay. Okay. And try to name these two. And check the aromaticity of these two. So those are the ones we call aromatic ions. Obviously they are all aromatic, but it's in ion form. So just try to I'll give about 2 minutes. Okay, so what's the name of this one? Do you guys remember this one? So we have cyclopentene, but you have two double bonds over here. So this will become 1, 3, cyclo, penta, two double bonds, right? So we diene. Okay. Do you guys remember this? 1, 3, cyclopentadiene. Because we have 5 carbons in the ring. We have 2 double bonds, so we can do 1, 2, 3, 1, 3, as you're locating where there's two di in the double bonds here. So this is a 1,3 cyclopentadiene. But the thing is, you have a lone pair here. Okay. Actually here. Okay. So in this case, you can do all same, but it's the negative charge, so it's anion. But this is anion, but of this compound, so we put YL. So this is a cyclopentadienyl anion. Okay. So this one is pretty much the same. We're gonna have a cyclo. So 7, right? 7 carbons in this ring. So it'll be what? Hepta, and you have a 3, not 2, right? So it'll be triene. Okay. But you have a cation over here. So we're gonna change this one to once again YL. And this cation now, so it'll be cation. So it's a cyclopentatrienyl cation. And then I just want you to remember, because of this lone pair and there's no electrons of P, that still makes the 6 pi electrons in this structure, ring structure. And here, 1, 2, 3, 4, 5, 6. There's nothing there, so 6. So this is why, and even though ionic molecule form, there are aromatic ions. They're all aromatic compounds. Okay. You guys remember this, right? We did it like 2 weeks ago, maybe. All right, let's move on to. Okay, so we're just gonna do one example. We don't have enough time, but maybe. Okay, can you guys tell me if this is aromatic or not? It says one example of what? Heterocycle or heterocyclic compound. Do you think this is aromatic or not? So you have so we follow the Hocker's rule, right? 4n plus 2 rule. So if you have either 2, 6, or 10, so on, of numbers of pi electrons, they'll guarantee that that compound is the aromatic. But if you have a double bond, obviously they have electrons at each. So it'll be 1, 2, 3, 4. This lone pair will stay on this p orbital and the nitrogen. So there will be obviously 6 pi electron that can be conjugate. So that shows very good aromatic species. Then we can do another one. Slightly tricky because you have a 2 lone pair, but in this case, this lone pair will be in sp2. So we talked last week. So only one pair of electrons, which is 1 lone pair, will be in Connes, and the other p orbital pi electrons to be conjugate, which only makes 6, not 8, because the other lone pair will be in sp2 hybrid orbital on those 3. Okay? So only 1 pair, so that makes 6 again. So this is also aromatic compound. So this is just a quick review we did last time. Okay. There's you want to try one more here? One more, that's good. So then, could you tell me if it's aromatic or not? So you have a 2 lone pair. So do you think it would be aromatic or not? Aromatic, right? Perfect. Because once again, those 3 will be kind of a hybrid, and only 1 pair of electron will be used for conjugating. with other pi electrons on the double bond. So that still makes 1, 2, 3, 4, 5, 6. 6. So this also satisfies the Hepta's rule, which is one of number 2, 6, 10, that's 6. Okay? So it's also a number. Great. Okay. So I'll move on. There's only one more question I want to go over for the exam, and that's it for the third review session today. So there will be only one question for the complex splitting NMR question, is this one. So if you just memorize this question today, you get the right answer on the exam. So I'll give you this exactly same question on the exam. So the question is the same question you're going to see on the exam on Wednesday or Friday is the number the peaks on these three. Okay? So those you have a 3 signal because they're all not equivalent to each other. So you have a different position where you can find the signal, and tell me how many peaks on each. So maybe this is maybe triplet, doublet, or quartet, or that's one question. Exactly the same question will be on the exam. So this is a complex split. It's kind of a tricky one. So I'm not gonna make any difference here. I'll give it exactly the same question on the exam. So the question was, you have a 3 hydrogen here. This is the proton NMR. You have a 3 signal for each. It's 1, 2, 3, 3 signals. They're not equivalent to each other. And how many peaks on each signal you will see there? That's the question. I'll give you about 1 or 2 minutes, and that'll be all for the review today. You guys did great so far. Okay, we're almost done. Okay, so maybe 30 seconds, and we'll do this together. Okay, so let's try to do these two first, okay? So you have this signal here. And then, do you guys remember n+1 rule, right? n+1 rule. So if you have the hydrogen over here, there's neighboring carbon and numbers of the proton attached to it, just +1. That's the number of peaks you're gonna see on that signal. So if you have this proton over here, you have only one neighboring proton here. So n+1, that gives what? 2, right? So you'll see for this signal will be doublet. 2 peaks on that signal, okay? Makes sense, right? Okay. So this one here, this one, there's no proton attached to it. Do you see, right? 1, 2, 3, 4. There's no proton here, but there's only another proton, one proton over here. So it also has only one proton neighboring in this carbon here. So it will be also doublet here, doublet here, okay? So that makes this hydrogen will have how many? It have a 1, 2 neighboring protons, so it'll be triplet, right? Then there will be wrong. So I want you to remember this one. So the answer for this one is 4. 4 peaks will be there because the 1 plus this proton will be split by 2 different protons. So it has 2 neighboring protons, but these protons are not in the same chemical environments. So the way they splitting the peaks on this signal is different. So it doesn't follow the Pascal's triangle. That's why you cannot use n+1 for this one, but you need to put n+1 times n+1 rule. So you have a 1, it doesn't matter which one is mn, doesn't matter. n+1 is 1 plus 1, 1 plus 1, that makes what? 2 times 2, right? So you're gonna have a 4 peaks over here, quartet. So doublet, quartet. And this is the exception, we call this complex splitting, because this signal will be divided, split by two different coupling constant, meaning the way that spreading the peaks is different. So you can just do n plus 1, but n plus 1 times n plus 1 instead of before. But this exactly the same question will be on the exam. So please remember this one for this. So be 2 peaks on here, 2 peaks on here, but 4, okay? Not 3. Okay? That's it for today. Okay, thank you guys.